Namaste to all JVNs, myself JVN Dr. Khushbu Umar. Today we will discuss about enzyme kinetics. What is enzyme kinetics? So basically how enzymes regulate any chemical reaction is known as enzymatic kinetics, and in the enzymatic kinetics there are various kind of mathematical proportions by which you can calculate the rate of reaction and total substrate and total product formation in the enzyme kinetics technique. So quantitative measurement of the rates of enzyme catalyzed reaction or a systematic study of factors that affect these rates. Enzyme kinetics begins in 1902 when Adrena Brown reported an investigation of the rate of hydrolysis of sucrose as catalyzed by the yeast enzyme invertase. Brown proposed that overall reaction is composed of two elementary reactions in which the substrate forms a complex with enzyme and then that subsequently decomposes to product and enzyme. Here we can see in the flow diagram E, which is enzyme, S is substrate, is going to make a complex ES, and then it will be break down and produce a product, and the enzyme will be separated from this. According to this model, when the substrate concentration becomes high enough to entirely convert the enzyme to the ES form, the second step of the reaction becomes rate limiting step. The overall reaction rate becomes insensitive to further increase in substrate concentration. The general expression of the velocity means rate of this reaction is V is equal to dP divided by dt is equal to K2 ES. The overall rate of production is production of ES, difference between the rates of elementary reactions leading to its appearance and those resulting in its disappearance. So here we can see E plus S is equal to ES, and then it will create P and E. So DES divided by DT is equal to K1 E and S minus K minus 1 ES minus K2 ES. At this point, an assumption is required to achieve an analytical solution. The rapid equilibrium assumption is Michaelis-Menten approach, and the steady state assumption is given by the Briggs and Haldane approach. Michaelis-Menten approach. The rapid equilibrium assumption, and it assumes a rapid equilibrium between the enzymes and substrate to form a ES complex. Means K1 E and S is equal to K minus 1 is ES. The equilibrium constant, which is Km, can be expressed by the following equation in a dilute system. Means Km is equal to K minus 1 divided K1 is equal to ES divided by ES. Since the enzyme is not consumed, the conservation equation on the enzyme yields is equal to ES is equal to E0 minus ES. Then rearrange the equilibrium constant equation, means Km is equal to K minus 1 divided by K1 is equal to ES divided by ES. On the other hand, ES is equal to ES divided by Km. Substituting E in the above equation with enzyme mass conservation equation is equal to ES is equal to E0 minus ES into S divided by Km. Next one is equal to ES is equal to E0 minus ES into S divided by Km, and in the next step ES into Km is equal to E0S ESS, and at the end ES is equal to E0S divided by Km plus S. Then the rate of production and formation V can be expressed in term of S is equal to V is equal to dP divided by dt is equal to K2 ES, and where V max is equal to K2 E0. Now come to the steady state assumption, which is SSA. So progress curve of the components of a simple Michaelis-Menten reaction except the transition phase of the reaction before shaded block ES remains constant until the substrate is nearly exhausted. Hence, synthesis of ES must equals to its consumption over the course of reaction, that is ES maintain steady state. This is the defined Km Michaelis constant and ES reaction. If we talk about the Michaelis-Menten equation, it is equals to like Vs is V is equal to Vmax into S divided by Km plus S. Michaelis-Menten equation, the rate equation for a one substrate enzyme catalyzed reaction. It is a statement of the quantitative relationship between the initial velocity V0, the maximum velocity Vmax, and the initial substrate concentration S, all related through the Michaelis constant Km. Numerical relationship emerges from the Michaelis-Menten equation in the special case when V0 is exactly one half of Vmax. Means Vmax divided by 2 is equal to Vmax S Km plus S. On dividing by Vmax, we obtain 1 by 2 is equal to S divided by Km plus S. Solving for Km, we get Km plus S is equal to 2S, and Km is equal to S. So when V0 is equal to 1.5 Vmax. What is Km? So Km is the substrate concentration required to reach half maximal velocity, which is Vmax divided by 2. Km is a measure of a substrate affinity for the enzyme. A small Km means the substrate binds tightly to the enzyme and saturates the enzyme. What is Vmax? Considering the total enzyme concentration, the maximal rate that the enzyme can attain is Vmax, and Vmax is equal to the product of the catalytic rate constant, which is K cat, and concentration of the enzyme. The Michaelis-Menten equation can then be rewritten as V is equal to K cat E S divided by Km plus S. K cat is equal to K2, and it measures the number of substrate molecules turned over by enzyme per second. The higher the K cat is, the more substrates get turned over in 1 second. This is the Michaelis-Menten kinetics graph, and here we can simply see that E plus S is equal to ES, which is the complex, and after it will be break into E plus P, which is P is equal to product. Assumes the formation of enzymatic substrate complex, and assume that the ES complex is in rapid equilibrium with free enzyme, and breakdowns of ES to form products assumed to be slower than formation of ES and breakdown of ES to reform E and S. Here we can see again formula V0 is equal to Vmax into S divided by Km plus S. Ka is an equilibrium association constant. Unit is m molar, and Kd is equal to E into S divided by Es. Kd is an equilibrium dissociation constant, and tight binding implies a low dissociation constant and high association constant. Transformations of the Michaelis-Menten equation, the double reciprocal proof. The direct measurement of the numeric value of Vmax and therefore the calculation of Km often requires practically high concentration of substrate to achieve saturating conditions. The Michaelis-Menten equation can be algebraically transformed into equations that are more useful in plotting experimental data. Here we can see Lineweaver-Burke equation, and equation is the equation for a straight line y is equal to ax plus b, where y is equal to 1 by v0 and x is equal to 1 by s. A plot of 1 by v0 as y as a function of 1 by s as a x therefore gives a straight line whose y-intercept is 1 by Vmax, and whose slope is Km divided by Vmax. Such a plot, called a double reciprocal or line-Wheeler group model or plot, setting the y term of equation equals to 0 and solving the x, reveals that x-intercept is minus 1 by Km. Linear group plot has the great advantage of allowing a more accurate determination of Vmax, which can only be approximated from a simple plot of V0 versus S. The double reciprocal plot of enzyme reaction rate is very useful in distinguishing between certain types of enzymatic reaction mechanisms. Kinetics of isomeric enzymes. Isomeric enzymes with only one enzyme conformation, the efficiency of substrate binding declines constantly with increasing A, because the number of free binding sites is constantly decreasing. Allosteric enzyme, the binding efficiency initially rises with increasing A because the free enzyme is present in a low affinity conformation, which is gradually converted into a higher affinity form as a result of binding with A. It is only at high A values that a lack of free binding sites becomes noticeable and binding strength decreases again. Now come to the enzyme kinetics factors. So catalytic properties of enzyme and consequently their activity are influenced by numerous factors. These factors include physical quantities, chemical properties of the solution, means pH value, ionic strength, and the concentration of the relevant substance, cofactors, and inhibitors. The effect of enzyme is strongly dependent on the pH, and activity is plotted against pH. A bell-shaped curve is usually obtained, and bell-shaped of the activity pH profile results from the fact that amino acid residues with ionizable group in the side chain are essential for the catalysis. Next one is the bisubstrate kinetics. So most reaction in biological system usually include two substrates and two products, means A plus P is equal to P plus Q. In bisubstrate reaction, transfer of a functional group such as a phosphoryl or ammonium group from one substrate to another. So the in oxidation reactions, electrons are transferred between substrates. Multiple substrate reactions can be divided into two classes: sequential displacement and double displacement. In the sequential displacement, all substrates must bind to the enzyme before any product is released. Sequential mechanisms are of two types: ordered, in which the substrates bind the enzyme in a defined sequence, and second is random. Many enzymes that have NAD plus or NADH as a substrate exhibit the sequential order mechanism. Lactate dehydrogenase reduces pyruvate to lactate while oxidizing NADH to NAD+. If we talk about the sequential displacement, so in the ordered sequential mechanism, the coenzyme always binds first and lactate is always released first. Random sequential method or mechanism, the order of addition of substrates and release of product is random. For example, formation of phosphocreatine and ADP from ATP and creatine, a reaction catalyzed by the creatine kinase. Sequential random reactions also can be depicted in the notation. If we talk about the bisubstrate kinetics, here we can discuss about the ping pong. In double displacement or ping pong reaction, one or more products are released before all substrates bind to the enzyme. Mechanism in which the first substrate A is bound and immediately cleaved. A part of this substrate remain bound to the enzyme and is then transferred to the second substrate B after the first product C has been released, and this kind of a process is known as ping pong. The enzyme aspartate aminotransferase catalyzes the reaction of transfer of amino group from aspartate to alpha ketoglutarate. So this is the sum up of this session, and this session is powered by digital version 2.0 JAYOTI VIDYAPEETH Women's University. And if you have any query, then mention in the comment box. I will resolve it. Thank you.